let's talk about some hurricanes. So, hurricanes, natural disasters, they cause a lot of problems around the world. $153.9 billion of damage in 2016 alone. No one is immune to weather emergencies, right? Are people prepared? Right? Whether it's a hurricane or it's a tornado or it's a flood or a snowstorm, everybody needs something, right? And sometimes people need a lot of things. But what do, right? You go to the grocery store, the shelves are empty. You go to your local hardware store and you need a tarp for your roof and they could all be gone, right? Empty shelves don't help anyone. There's a lot of opportunity around this. How do organizations and businesses change the way they operate so they can quickly react to these types of storms to meet people's basic needs, right? Obviously, there's chances to increase revenue. There's obviously chances to lower transportation costs. A lot of times in these scenarios, supply chains get disrupted and you end up paying what's essentially the same thing as overnight shipping to get your product to your stores, and it costs a lot of money. And then you also have a chance to make a real difference in people's lives, and you have a chance to really have a lot of increased customer loyalty. You can really win customers for life if your organizations can get this right. But obviously, it's not easy, right? There's a lot of real-world constraints that come into play here, right? You don't have every product that you need in every store and every distribution center. Like I mentioned, logistics, the costs are expensive, and there's often a very short window of time. If you're talking about a tornado or a wildfire, you'd have hours maybe of notice. In the case of a hurricane, maybe you're lucky enough that you've got a couple days, and so an organization has to be able to react very quickly. But you also don't know which products you need to send and then how much and when. So that's what we're going to talk about today. So quickly, who are we? We are North Highland. We are a full-spectrum expertise management consulting firm, mid-sized, located in Atlanta, Georgia. And we go to market across 4 different service lines: customer experience, performance improvement, tech and digital, and transformation, with these 8 capabilities. And the 3 of us presenting today are in the data and analytics capability. Okay, how do you respond to this as an organization, right? Didn't come out right. So we're talking about a model today, right? We're talking about a predictive model. And with any predictive model, even if it is the most accurate model in the world, somebody has to do something with that number, right? Somebody has to operationalize it and make it happen. And for a large enterprise, there are many components that have to be pulled together to make that happen, right? Product prediction, that's what we're here to talk about today. But other things such as ownership and decision making. Who is going to say if that's the right amount of product to send to a store, right? What approvals have to happen? Having some kind of central command where people are all in the same room to make these decisions very quickly. All the different trans and freight issues around diverting freight from different locations. Having contracts in place for shipping in these situations so you're not paying spot market prices. Obviously, communication and visibility is very important. IT system uptime, right? Everything runs on a system. If you can't get these orders plugged into some kind of system, it's not going to result in a truck roll. And store ops resilience, this is a big one, right? So if you've got a store out there, a hurricane just went by and the roof is ripped off, how do you know? Are your people going to be able to show up? If they can show up and your store is intact, customers are going to start showing up. What happens if you only have some of your employees show up or they're home helping their families, right? What if they don't have power? All these things happen, and so people need to prepare for it. And finally, customer engagement. If you can do hyper-local communication with your customers to say which stores are open, which stores are closed, what products do they have, what products are they waiting on, you will definitely resonate with your customers. Okay, the business case. There's a lot of opportunity here. We looked at a number of investor calls throughout the last number of years where there have been a lot of hurricanes. And you can see there are big numbers we're talking about. $360 million of hurricane-related sales in 2011. I believe that was Hurricane Sandy. Second quote, significant demand on the transportation system and costs went up. This is the C-suite of very large companies. Hurricanes Harvey and Irma drove demand, and our team sent over 11,000 truckloads of product for 2 storms in 2 cities, 2 states. To take that one step further, to talk about the actual revenue impact. So this is from the end of last year, again for Irma and Harvey, different retailers and the impact it had on their revenue. You can see you've got a lot of home improvement companies up at the top. Clearly they have a lot of revenue to gain. And then you've got some others lower on the bottom there where maybe they don't, such as Macy's and Kohl's, don't necessarily sell a lot of generators or tarps or flashlights and batteries, but they are impacted just the same. Maybe they need to work on their store ops resilience or come up with their transportation plans where they need to adjust those to reduce cost. But that is not what we really came to talk about today. We want to talk about a little bit of the technology, and here to go into the prediction is my colleague, Charlie Moore.
How did we make this happen? How did we build a model that can effectively predict demand in near real time based on very confusing situations on the ground? Well, Google Cloud Platform has enough tools to make a system like this possible to build. Everything from a big data platform, data warehousing system in BigQuery and cloud storage, to the machine learning tools that are enabled through Cloud ML, TensorFlow, scikit-learn, and Keras on top of that, to orchestration layers like Kubernetes that let you run massive processing loads at a moment's notice that can scale up and down and be efficient in their processing. It gives us a very easily deployable, maintainable, highly reliable system that we can work with. One of the biggest problems that we had coming in, and we knew we were going to run into this, was getting all the weather data. If you don't know where a storm hit, almost exactly, how can you predict hyperlocal demand? If a hurricane moves by 50 miles, you might be sending generators to the wrong store. So you need to understand exactly where demand is going to be by understanding what the weather is. There's a big problem with that, though. Turns out, when a hurricane hits, all of the meters and sensors that the National Weather Service has out there fail. They stop reporting accurate wind speeds, they stop reporting total rainfall, and you just get nulls in your data set. Actually, NOAA has a great data set that's available for free in Google BigQuery. We looked into it, and it turns out during all of the key hurricanes that we were interested in training on, there were big old blanks in the data. But NOAA does provide real-time forecasts, and you can get current hour forecasts that essentially reflect the reality on the ground. But those are in an interesting file format, and they can't just be dumped straight into a database. So we need a processing tool that we can use to get the data from NOAA into BigQuery. So how do we do this? Each file is programmatically named based on the time, the forecast that it's running, as well as the number of hours in the future that the forecast is for, because if something is happening right now, sorry about that. If an event is happening right now, we want to be able to understand the impact in the future as well. So we can generate a URL from the date time that we're interested in predicting and download from NOAA and process that in, actually, it's a Fortran library that has existed since, I think, 1982. So we need a specialized environment that can run Fortran. We can't just run this in a Node app engine or something like that. Then we will dump the results into a CSV and stream those records into BigQuery. 24 files per day for 10 years results in about 150 billion records that we're having to load in order to train the model. So we used Docker and Kubernetes in this case to do our deployment strategy. There are a lot of different technologies you could use to do this. As an organization is moving into a cloud environment, they're going to have guardrails put up, right? You have to work within the constraints that are set by security and reality on the ground. And Kubernetes was a really good tool that was in our allowable toolbox here. So we developed Python programs, 2 of them actually, to just do the quick streaming and land in Kubernetes. Now, if you've been to many talks this conference, you've probably heard about Kubernetes. And most of the talks are about Kubernetes as a microservices handling layer. You can deploy a bunch of different microservices into Kubernetes, and they will scale up, scale down. That's actually not what we're doing here. We only have 2 services in this, and neither of them are micro. We're just using Kubernetes for raw computing power, and we don't have to manage anything. So we have a Redis pod that we spin up. That has a list with all 10,000 files that we want to download. And we spin up about 500 different computers. Each processing task is very small, so we only need the G1 small compute engine type. It's very inexpensive. And we can actually make those nodes preemptible as well to lower the cost even further. Redis gives us a very fault-tolerant system to work in. It's very fast. And this is all the code that it took to spin up 2 jobs. One on the left, you've got our Python script that's going to do the downloading and processing. And on the right is just an example of how you would spin up the Kubernetes cluster. That's pretty much all the work that we had to do from the management and orchestration side. It saves a lot of time. It's really clean and nice to work with, and you don't have to know MapReduce, which is also nice. So Matt's going to come up in just a second to talk about the details of how we do the prediction, but just to give you an idea of what we're predicting. We're looking across 300 product categories for a retailer, and we're trying to understand what is the change in dollar demand in that category. You know, if I want to buy a mop, how much is the total dollar demand going to increase? Well, you might have multi-packs of mops, you might have single packs of mops, multi-packs of bleach. So by distilling it to the dollar level, you're able to get a good insight into what is the actual consumer need in this area. How much product do we need to ship? If we look, and this is a noisy graph, but I'll explain how it works. If we look at the way demand actually works in a store, the blue line is the real customer demand. These are people coming and knocking on your door and saying, I want to buy something from you. A traditional replenishment system is not fast enough to respond to that demand, because leading into an event, you will have what's called pre-strike, where the demand is increased immediately before the hurricane comes. I bet a lot of people here have gone out and bought flashlights or batteries right before a hurricane is coming just in case you lose power. Additionally, you're going to have a second demand spike when the event really happens. And that's the one that's really hard to respond to and predict. The yellow line that you see here is the amount of days of stock that a traditional replenishment system might leave you with. Ordinarily, it works well. It keeps you around, whatever baseline you set for your replenishment system. It keeps about that many days of stock on hand. Maybe you get a shipment every 2 weeks of mops. But in these severe events, that demand is going to increase way too quickly, and you'll very, very quickly be out of stock. You won't have what you need on the shelves for people to buy, and then you'll have too much. After the event, your replenishment system has caught up, and now all of a sudden you've got 2 or 3 times the inventory that you want to have on hand. For mops, this may or may not be a big deal, but think about a high-cost item like a generator. If you ship a pallet of generators to the wrong store, you have inventory that you can't sell in the wrong place, that you may have to ship to another store that actually needs it, but by then it might be too late. People aren't buying generators anymore because their power's turned back on. And so now you've got a bunch of extra stock that you either have to mark down significantly or send back to the distribution center or something like that. So we looked into how we can predict this, and we came up with a lot of options. We looked at traditional time series analysis. We looked at linear regressions, things like that. None of those can handle the scale and volume of data that we were considering. We really needed something that could be rapidly scaled up and accurate across the depth of data that we're looking at. To give you an insight into the modeling techniques that we used, we're going to bring up Matt Yates, who's my colleague.
I had a lot of energy around this project just because the opportunity to really impact people's lives, to meet people in a time of need. And it was a lot of fun, too, because we got to really be on the bleeding edge. Loved interacting and working with Google Cloud Platform. This was one of my first interactions. So I think the two themes that we've heard about Kubernetes and about machine learning and AI at this conference really continue on, and we really experienced the benefits of those things as we'll go through here. So just kind of give you a sense of what our pipeline looks like here is we had to build out a ton of features in order to be able to give you a accurate prediction. So we've got features in here. We'll go into really detail around what we're doing there, but we've got Kubernetes pulling in that weather data. We've got BigQuery, which is housing a lot of internal company data. We're augmenting that with census data and some other really rich open data sources. Putting those into models, training them. TensorFlow and Keras have a little bit of scikit-learn in the pipeline there as well, in the pre-processing. And then ultimately, all of that gets wrapped up into an output prediction. So let's deep dive on some of these. On the actual features, weather, we knew right away we're going to have to collect that. We went and got billions of records, put them in BigQuery, was able to roll those up into a store hourly grain in BigQuery in the matter of minutes. So you're talking about terabytes and terabytes of data, billions of records. We sort of arranged it into store using trade areas, zip codes. So we needed to go from an individual weather dot on a map to a zip code, assigning it to a store, and then rolling all of that up to a store hourly actual or forecasted weather. And BigQuery handled it effortlessly. It was spectacular. Beyond that, we went out and got NLCD data, that's National Land Cover Database. It's a governmental agency that publishes, basically they go through satellite imagery, turn that using some regression tree, or excuse me, classification tree models into information around what's the tree cover like, what's the impervious surface percentage at any particular point at a 3 meter grain across the US. They also have a really rich, I think it's 18 category data set about, for this point on a map, is this high urban density, low urban density? Is it, is it ice or is it a farmland? So some really rich data around what is happening on the earth at a particular point. And we were able to aggregate that up at the store level to say what percentage of the store's trade area is covered by farmland versus high density urban housing. And that's going to make a difference in what sells ultimately following a storm. Census data, widely available, population densities, pulled in a lot of really cool information from the census as a potential feature, and then inventory sales data from our client. So one thing that I really wanted to point out here was we did almost all of our feature engineering in BigQuery, and I absolutely loved working with it. SQL worked 95% of the time. We found a couple of instances where we wanted to use JavaScript in a user-defined function. So I've got a little example here. Our project was beyond hurricanes, so this is a tornado example. But it would be pretty difficult in SQL alone to, given a latitude, longitude, of a tornado, find all of the stores associated with potential impact from that tornado, find their distance, rank the distance, take some pretty complex geometry, trigonometry. I had to go back and remember some stuff from high school to do this. But I was able to create a user-defined function, call that user-defined function in SQL, and create some really complex calculations right on top of BigQuery. Very fun stuff. So then, once we did our feature engineering, we needed to train those models. We went in here thinking we could sort of create one model to rule them all. So we're thinking RNN, so we have some time series. We're thinking multi-output, so we have all these product categories. Let's predict them all in a single model. We experimented with that. We were able to get a skillful model. It was about twice as good as a naive model of just a moving average. So if a moving average model said you'd have $200 worth of sales, and we might be $200 off with that, and our model with our RNN was able to predict that twice as well. But we weren't satisfied with that. We thought, we can do better if we may dissect the problem a little more. So ultimately, we ended up creating just a sequential feed-forward neural network, and actually dividing it from multi-output down to a single output, and then just creating a lot of those little deep networks and calling them individually. And then when we create the prediction, we can call each of those models individually in serial or parallel, and we're able to make those predictions for each product category using a similarly architected neural network, but just with the discrete weights. So initially, we're using TensorFlow. We were feeding the data in with a queue runner, and because with RNNs, you've got pretty complex data sets, very big data sets. Ultimately, we found, if we want to try to make this as skillful as possible, let's try to iterate fast. So in comes Keras. We're able to iterate and try things out in Keras. It's fully compatible with ML Engine, which we'll talk about here in a second. So we moved from pure TensorFlow to a Keras library on top of that with a TensorFlow backend to do some rapid prototyping. And the way that we sort of reframe the problem here is instead of trying to do an RNN and a time series analysis, we said, every one of these events has a time zero when the event actually happened. We need to go figure out what our baseline cells were in the days coming up to that. We need to figure out what our pre-strike cells are, if that's applicable, and that's something we might want to predict, and we want to also predict our post-strike cells. And the good news is, with a weather forecast, if I trust the forecast of the weather, and we weren't trying to forecast the weather, we were consuming that from NOAA, the National Oceanic Atmospheric Administration. I can actually, days ahead of a hurricane actually hitting, I can give you, according to the weather forecast, where's that hurricane going to hit, and go ahead and predict post-strike demand right after that. And then we pulled the time together. So instead of trying to do a time series demand forecast, we said, let's take all the demand that's going to happen in the immediate period following the hurricane, lump it all together, and say, after this hurricane, here's going to be your demand level, and it's going to be spread out across time. But we kind of divorced the time element from our problem, and we're able to get a more skillful model that way. So then, once we got our architecture how we wanted it, we used hyperparameter tuning in ML Engine, another brilliant feature of Google Cloud. And so here, we were able to tune and sort of grid search our batch size, learning rate, number of layers, the shape and size of our layers, and our activation function to find the optimal, most skillful set of those to make our predictions. So here is a slide that we're really proud of. So as we said, we have 300 different product categories. The product categories are really based on consumer need. So mops are a category. Dehumidifiers are a category. And we have a lot of products that a retailer might have within each category, but we're predicting demand for mops, demand for dehumidifiers. And in the end, for our post-storm predictions, we were able to get 90% of predictions within $150 daily average error. Meaning, and that's based on a holdout set, meaning, if we predict it's going to be $300 in sales, 68% of the time, it's going to be between 250 and 250 and 350. So pretty accurate there. We were really pleased. Our client was really pleased with the accuracy on the holdout set. And I think that's a function of a lot of time spent in feature engineering, data pipelining, as well as the power of deep neural networks. And then ultimately, I think one of the major challenges here, and you'll hear about it in all of the DevOps or ML conversations, is actually getting this deployed and operationalized. Ultimately, this is sort of a structure we think is the best to keep this going on long term, using container registry, Kubernetes, obviously source control, BigQuery is where all that data lives, and then we stored out all of our models in Keras in H5 format to cloud storage. We're able to call those back and make those predictions in really almost real time. I mean, each prediction takes seconds to make, and that's, the interaction between cloud storage and BigQuery and your compute environment is really seamless there. So I'm going to call Dan back up. He's going to talk about how do we take these predictions and actually make them operationalized on the ground.
Thank you, Matt. Okay, so we've got a very accurate model now. It's putting out numbers that we believe in and that we're ready to take action on. So back to my point earlier, great, how do you fold this back in? What do you do with it, right? A lot of things have to happen still. First of all, a person still has to be in the loop here, right? Like any model, this is a prediction. It has a confidence to it, and the confidence can be high or low. So somebody needs to say, this one's wrong, we need to change it. There's also other factors that come into play. Maybe the prediction is right on, but the DC doesn't have the inventory, or there's an event coming up at the store next month and they don't want to sell all the inventory this month. A lot of other factors that come into play. The model doesn't know everything, right? Person's got to be involved. And then once the person approves it, it's got to get out the door, right? So it's things like, how do you fit it into your ERP system to cut a purchase order? How do you then get it on a truck, right? You've got to, you might be shipping, your company might use pallets or you might use cartons, right? How do you get the right number into those units and on a truck and out the door? Right, there's a lot of rounding that goes on in these scenarios. So I thought I would walk through an example. And again, all of this is done in BigQuery. So let's say, like we mentioned before, we're doing sales at a category or grouping level, right? In this case, I'll use generators. So let's say for a store, we know that we're going to need $10,000 in generators. And we say that because we don't necessarily know if it's this particular generator that people really want to buy or that one. At the end of the day, people will often buy whatever generator is there if their power is out. And so we predict at the group level. But we ship at the item level, right? And so we've got to get this down to an item. And there's lots of ways to do this. To turn this into an individual SKU, you can do a number of things. It depends on your organization. So maybe you want to default to what that store's customers prefer. Maybe they really love the 5,500 watt generator, right? Or maybe we're talking about another category, say shingles, where in this part of the country, they really like architectural gray shingles. But in another part of the country, they like tan shingles, right? And so you really have to be able to fine-tune which actual products you're going to send to the store. Obviously, you have to check the store's inventory. Maybe the store has everything you need, and you don't need to ship a thing, right? So again, we're talking about BigQuery taking this prediction and going in real time checking store inventory. Maybe they don't have enough, but there's a truck on the way. You've got to know that too, obviously. Maybe even after that, you still need some, and so you have to see if your DC has enough. Maybe your DC has enough for your store, but doesn't have enough for all the stores that DC serves. What do you do in that case, right? Then let's say you figure that out. You still got to round for how many do you put on a pallet? How many pallets do you put on a truck? right? Maybe the recommendation is you need, what do we say here? You need 2 pallets of the 5500 watt. Well, maybe that was 1.9 pallets that you really needed. You're probably going to round that to 2, right? You're not going to slow the truck down. You're not going to slow this process down to get that right. You're going to move and go, right? So how do you handle that logic very quickly? Supply chain organizations do this stuff all the time, and the more we can help them get there faster, the whole faster this whole process works. And so you see at the end here, the net SKU sales prediction ends up being significantly different than what came out of the model. And so just to talk about data volume here, imagine for a large company, the size of the table that has the SKU store inventory. Think of the same thing for DC inventory. Think of the same thing for POs, right? You've got to hit billion row tables over and over and over again, and you got to do it fast. And BigQuery was, again, pretty awesome at doing it. Okay. Again, so I'm on the how do you operationalize this notion here. So you take a model that's complex, and we didn't build this to run this forever. We built this to hand over to our client, and so they often have a varying range of skill sets and knowledge about data science to where you've got to tailor your solution to the people who are going to receive it. Also, there's a complexity issue here. Like, we could probably get the 90% accuracy up to 95 or higher if we baked every single thing we could in the model, took everything into consideration. But then we risked it being so unwieldy and cumbersome that nobody would even remember what all these configuration parameters were. And so we had to right-size it, right? And so these are just some examples. And so these are some of the tunable parameters. We call them knobs. We gave them a lot of knobs to turn of how they can say, you know what, I want to adjust this, I want to adjust that, to give them the right level of granular control without having to crack open the code and get their hands dirty. They can do that if they want, but if they don't, they've got a very easy way to say, you know, that last shipment we sent, it was a little too much or it was a little too little, let's make some changes. So you see some things like max wind gust threshold, right? Maybe there were some events where we didn't really recommend anything because we said they didn't hit a threshold. Well, we could maybe lower that number and more events will pop up. And with that, I'm going to pass it back to my colleague, Mr. Matt, who's going to show you some demos.
So ultimately what we're going to demo here is the end user interface, just so you can get an idea of how this would be done in action. Most of these numbers are made up so they don't tie out completely, but just for client confidentiality purposes, but this will give you an idea of what we're looking at. We decided to use Tableau for these demos. Love working with Tableau for just a quick dashboarding tool. And so we'll give you a sense of both how do you look at weather data and understand what's happening on the ground at a store? How do you turn your weather data into predictions, and how should you consume that as a user? And ultimately, after you turn those predictions into orders, how do you track it? So what you're looking at here is the weather aggregated to a store level. This is actually for Hurricane Irma, I believe. So you'll see all the stores listed there on the map. If you click on a store, you can get a data table here that shows over time some key weather metrics. So in this circumstance, wind gust here was 119 miles an hour on September 12th at noon, and that was actual for one of the Florida Keys. That was the actual wind speed. We've got a suite of metrics here from total precipitation, temperature, vegetation rates, soil moisture that you could actually go through and look at and understand what was happening on the ground at each store. So I'm going to play this for you, and you can actually see the wind gust go up the coast, and it's on loop here, so you'll see it repeating over and over. And that is all wind gusts that we would consider to be an event that we need to consider potential demand spikes because of those events. So then once you know that, you want to turn that into a prediction. So what you're looking at here is the actual event prediction for an Irma example, 154 stores. I'm going to drill into a single store here. And we'll look at, for the products that are affected for this store, The baseline sales that we would have expected without an event, 146,000. We think we're going to get across all these product categories $310,000 worth of sales. We only have 135 on hand. We've got 33,000 en route. Therefore, we need to order $209,000 worth of product. That's $209,009 aggregate product, but it's split across a ton of item classes. So let's drill into some of these item classes and see what we need to order. And for our ACs and fans, we need to order 95,000 there. You can see we need 38 pallets, and our mean prediction error there is plus or minus 1 pallet. So if I'm a merchant and I want to be conservative about it, maybe I subtract a pallet, maybe I add a pallet. Same thing for tarps here. Our prediction error is really good at 0 on tarps. On grills, not quite as good, so we need 21 pallets, and that's plus or minus 2. And then let's drill in here on air quality dehumidifiers. So we need to send 3 of those pallets, plus or minus 0 on average, so pretty good prediction. So this is the store typically sells this 30-watt version of that at 31% of the time. But then in emergencies, you typically send a 50-watt. So we let the client choose, do you want to send the 30-watt, which is typically sold in that store, or do you want to send the 50-watt? So I'm not going to go into the actual ordering process here, just for confidentiality purposes, but then ultimately we turn those, how many do you need to order, into an order form that they could execute on their system. Then once you execute that order form, you want to be able to track that data and track those orders all the way to a store. So we built another dashboard that utilized all of the orders after they were placed all the way up until they were delivered. So some examples here of, you can drill in just like you can on any other Tableau dashboard we just saw into a particular product category for a particular store and see exactly what's headed to that store in both retail dollars and units. This could be used by the merchandising organization or it could be used by the store to understand what's on its way. And with the delivery ETAs and everything else right there on the page. So wrap this up. Machine learning plus a really deep understanding and integration with business process made this a successful project. Ultimately, I think a lot of you guys, probably not in the same category, but there's something to be considered here for the ability of how can you react and appropriately respond to human emergencies, whatever they may be, and help people and change people's lives for the better. So really appreciate your time listening today. We'll hang out over here in the corner if you want to ask any questions. And that concludes our presentation.